Okay, for a warm-up today, let's do a quick review of some polar that we learned last lesson. So take a minute, given this integral, I want you to convert it to an equivalent integral in polar coordinates. You do not need to evaluate. So go ahead and put this on pause and give it a try. Okay, so these, no matter what, we're going to need to start by sketching the region of integration. In this case, I'm going to interpret what these bounds mean to sketch that region. Okay, so notice this says I'm going to shoot an arrow parallel to the x-axis to start, because I have dx in here. And I can shoot that arrow anywhere where my y values are between square root of 2 and 2. So let me just shoot it here. And I'm assuming that's where my y values are between square root of 2 and 2. And this says that my arrow is going to enter the region along x is square root of 4 minus y squared. And so we had this actually in our last lesson, but if we convert this, this gives me x squared plus y squared, it's 4. And so it's this circle of radius 2. We're just doing the right half because I have the positive square root. And that's now where my arrow is entering the region. And then I'm going to look at where my arrow exits the region. And so that's from the top bound, exits at x is equal to y. So let's sketch that. X is equal to y, it looks something like this. And that's going to be where my arrow exits the region. And so one thing that will be helpful before we shade where this region is, it would be really helpful to figure out where this intersection point is. And so let's put those two equal to each other. So I have y equals x, and x squared plus y squared is equal to 4. And that's going to tell me that x squared plus x squared is equal to 4. 2x squared is 4. X squared is 2. X is plus or minus square root of 2. In this case, I'm just looking at the positive. So x is positive square root of 2, which means y will be also, because x is equal to y. Okay, that's important because we realized that I was allowed to shoot this blue arrow anywhere between y is equal to square root of 2 and y is equal to 2. So anywhere, those black lines that I put are the boundaries of where I can shoot this arrow. And everywhere on that region, the arrow always has to enter along the green curve, and then it always has to exit along the red. So that means this little kind of triangular shape is actually my region of integration. Okay, so that's hard for a lot of people to realize, and it's really talking about, can you translate what this means into a picture? All right, and we have to have that picture because now to switch to polar, we're going to resketch that picture. And now we're going to imagine what happens if we were to slice this instead of slicing in Cartesian coordinates, where I'm going to get little rectangular boxes. I'm going to slice in polar coordinates, where I'm going to get like those little spiderweb type graph paper. I'm getting those polar rectangular boxes. Okay, so now to switch to polar, I have several steps. I need to convert my integrand. So let's do the integrand first. In this case, I just have a 1 here, so that just stays as a 1. But then dx dy in polar, we know about this. And so in polar, we found that dA is r dr d theta. That was from last time. So I'm going to replace dx dy with r dr d theta. And that has to do with the fact that since I'm no longer chopping in rectangular boxes, but I'm now chopping in these little polar rectangles, that the area of a given polar rectangle is going to change and depend on r as I move out in the little spider web. So that was from our demo last time. Okay, and now let's get our region, or our bounds here. Let's do here. Okay, so R is, oh, I'm going to need a different color. Here we go. All right, so I'm going to shoot an arrow radially outward through my region and look at where it enters and where it exits. And so I start radially outward and I shoot it anywhere through my region. Okay, and look, it's entering when r is on the circle, so that's when r is equal to 2. And it's exiting always along this line. And so let's look at what this line is. This is the line y is equal to 2. And I need to write that in terms of r. We know y is r sine theta. And so that tells me that r is going to be 2 cosecant theta. That'll be my top bound. Okay, and then I need my theta bounds. And so those are going to be the smallest and the largest theta values where I could have shot this radial arrow. And so this will be my smallest theta value, which is occurring right along the line y is equal to x. And so that's going to give me theta is just pi over 4. And then the largest theta value is going to happen when theta is pi over 2. So this is now the equivalent integral, and these will have the exact same answers when we evaluate them if I had done this one or if I had done the one down below, because we take into account the fact that we change the area of the region we're integrating over. We take that into account with this little factor here, this r d theta, so we're going to get the same answer at the end. And then what's a geometric interpretation of this? When I'm just integrating dx dy up here, that literally is just going to be the area of the region R, which means that this will also have to be the area of the region R. We've just transformed it into slightly easier coordinates. Okay. Now, one question that comes up oftentimes with students is, how could I have figured out this angle, theta is pi over 4, if it wasn't something as easy as like y is equal to x? And so let me just show you a nice way to do that. If you had had a more complicated region, or a more, not such a straightforward slope, what you do is figure out, you're along the line, I basically look at exactly where this is occurring. And this is the intersection, if you notice, of y is equal to 2, square root of 2. Oops, let's go back. Y is equal to square root of 2. And r is equal to 2 from the circle. And so then I just rewrite that y in terms of polar. So y is r sine theta. And I realize I'm looking for the intersection points. So if I want the intersection point, I can literally plug in 2 for r right here. And that's going to give me 2 sine theta is square root of 2. And then I solve for theta. Sine theta is square root of 2 over 2, which in this case is telling me theta is pi over 4. But if it had been a less obvious angle, you could have done it just by solving for the intersection. Okay, so we're going to use this idea now and move on to today's lesson.